So we should be live now. We should be live now. Let me see. We're going to be inspecting Qiskit source code today, I think. Let me share this. How can I share this? Here. Copy. Let me just tweet quantum computing. I love quantum Twitter. Quantum computing. Hashtag quantum intuition. Quantum computing twice, sorry. Intuition. Can you guys hear me well? I don't know if there's anyone watching though, but if so, probably not, but so quantum intuition. Oh, come on, stop autocorrecting. So live now inspecting Qiskit's source code. Part 1. It's really just chatting, you know. I'm just gonna be playing around and browsing. So I kind of figure out that I kind of figure out that I wanted to basically you know, there's different ways that one can learn, right? And usually what people do is with things like Qiskit or Circ, like you kind of go like in a bit of a different way, right? Like you say, hey, like I learned something, and then I go and take a look at the tools that I have, and kind of see what, from what I've learned, what can I do with these tools. And so what I want to try to do today is a bit of a different approach to these, and I want to basically browse around Qiskit's source code and kind of try to see what's in there and see whether there's other stuff that I can learn from, or things that I didn't know that you could, I don't know, study or learn about quantum computing, right? Like, you know what I mean? Kind of trying to do it the other way around. So basically, seeing what's in Qiskit to see what else can I dig into in terms of quantum computing. So I hope that's going to be useful. I'm going to be doing more than these. I definitely, maybe it's not going to work. We'll see. I don't know. I kind of, let me see, because Qiskit, not the Slack, but like Qiskit, Qiskit.org, not the textbook. I don't want a textbook. I want the actual, maybe the documentation. Let me see. It's the microphone is working well. Okay, cool. Oh, what did I do? The documentation, exactly. So maybe I'm gonna take a look at this quickly first, because I want to try to understand what are the parts that Qiskit is made of, and where should I start? Because I know about these different sort of packages or layers, like the Qiskit Terra, Qiskit Air, and Qiskit Ignis and Aqua. But I don't really know, maybe, you know, I don't really know where to dig into first, where to start, like, because, so basically it says Terra is composing quantum programs at the level of circuits and pulses with the code foundation. IR is accelerating development via simulators and noise models. So okay, so this is what the simulators are probably. Addressing the noise and error. So Ignis is noise and error correction, I guess. And then Aqua is where you have algorithms and applications. And I guess Terra has the basics of Qiskit. And I don't know if I'm not like, okay, so here are the Qiskit elements. So there's a bit of a better introduction here, I guess. Okay, that's neat. So Terra is the basis, and then there's Ignis, Aqua, and Air. And then Qiskit Terra is organized. I hope you can read that. Qiskit Terra is So the Earth element is foundation which provides bedrock for composing quantum programs. So it's got circuit, it's got pulse, the transpiler, and then the whole provider thing. Okay, but if the simulators, okay, and the simulators are in another package, and then quantum info. Oh, so visualization stuff is also in here. Okay, so Terra is kind of the basics really. Air is. By the way, if there's anyone who's watching that kind of has, you know, questions, comments, topics, feel free to ask. I'm not really super strict here in terms of getting something concretely like done. Or if there's any parts of Qiskit that you'd like me to take a look at that you think kind of are cool, then we can also jump into these. I'm like, I forked. I basically forked the four things, and so Aqua, Terra, maybe who knows? Maybe I'm gonna even end up doing some kind of contribution to these maybe later in the series because I'm really planning to do sort of a set of live streams on these. Okay, cool. Back to the elements. So IRE has the simulators: Chasm simulator, static simulator, unitary simulator. Ignis has what? Noise, okay. Noise and errors. Null set of user parameters. These are then run on Terra. Feeders. So Ignis experiments, what is these? Are passed to the feeders module where they are analyzed and fit according to the physics model describing the experiment. Feeders can plot the data plus feed an output. This is something I have no idea what they're talking about. Like, so feeders and filters for certain Ignis experiments. The feeders can output a filter object. Filters can be used to mitigate errors in other experiments. Okay. So this is really, this seems to be really experiment-based kind of thing, where you work with experiments. I don't know. I really don't know. And Aqua is the element of life. It's where we need to find real-world applications. Blah blah. It's where the algorithms are. Okay. So Aqua is definitely interesting, but I don't want to maybe dive into this right now. I'm thinking about doing something new and fresh for me, which is the simulator stuff. I want to maybe take a look at like what those are, because these I'm not so much interested in the Terra part, but maybe we could take a look at this as well. The whole providers in the backend and stuff. Oh, but wait a second. Qiskit quantum info. To perform more advanced algorithms and analysis of the circuits run on the quantum computer, it is important to have tools to implement simple quantum information tasks, physical methods to both estimate metrics and generate quantum states, operations, and channels. Maybe I'll dive into this quantum info because maybe this is where. So what are more advanced algorithms and analysis? This is where I can get some of those kind of things where it's like I have no idea what is this about. And this is in Terra. Okay, so let's do this quantum info. And we can do simulators next time, I guess. So this is in Terra, is it? This is in Terra. And I'm thinking whether I'll just stay in GitHub or clone the thing. I might clone the thing. So git clone, cloning Terra. And what languages is this? And what is this written? Is it? It's all Python, right? Like, yeah, that's 99. Okay, that's 99.5% Python. Because I think the simulator stuff is probably written in like C++ or something. So we've got some examples. We've got what is in here? Track, pools, providers, quantum info. So quantum info is where we probably want to be. Okay. It's in the Qiskit folder. And okay, so there's no, that's where we want to go, because then there's documentation, there's examples, and there's test and tools. What is in tools? Probably some shared stuff. Okay, yeah. I think it might be easier using Visual Studio Code to browse around. We'll see. So I'm kind of waiting for these. And what are the examples in here? Python Chasm, circuit draw, initialize, QFT. Code navigation is available. Oh, really? So you can actually navigate to other parts of the code. Like, okay, interesting. Anyway, this is part of Qiskit. It's an example of the quantum Fourier transform. But why is this in Terra though? QFT circuit. Okay, so you've got like basically examples. Okay, so those are just examples. I want to go to Python IBM Q. What is in there? QFT. Level 0, level 1, level 2. What are those? Let me open them separately. So this is telling me that there's some buffering. Stream health, poor. But to be honest, I should have a good connection. I should have good connection. Why? Why is this complaining? Oh yeah, maybe because maybe because I was cloning these, so now I should now I should get better, probably. Yeah, I kind of feel like quantum info analysis. Maybe I'm better off staying in the browser. So far it's so where I was doing here, quantum circuit. No, using Qiskit Terra level 0. What is this? Example shows the most basic way to use Terra. It builds some circuits and runs them on both the basic Air local Qiskit provider or IBM Q remote provider. Okay, so more examples of using Terra. So those are just examples. Level 0. Level 1. What? My mouse is just going nuts. Cool. Bell circuit, blah blah blah. Those are examples, okay. Not like what's in the last example. This example shows an advanced user interacts with Terra. It builds some circuits and transpiles them with a path manager. Making the first circuit, making another circuit, setting up the backend. For backends, basically backends, print backend status, custom simulator, get custom simulator, print IBMQ backends, okay. Try least busy device, print all devices, blah blah blah. The path manager, I don't know what it is. Extend the data. Okay, so this is more advanced. Full and Scylla allocation, enlarge within Scylla, look ahead swap, decompose, swap mapper, simplify CX, enroll to single cubic gates. Ah, okay, cool. So you have a bunch of things you can. Okay, then you have assemble, show the results, run the job. Okay, stuff like this, yeah. Okay, well, let's go ahead and take a look at what's in the Qiskit in the quantum info, the quantum info part. Because here we've got analysis, operator states, and synthesis. That's something new. So average distance, make observable. What are these things? A collection of useful functions for post-processing results. Ah, okay. Interesting. So you can do average data, counts, observable, compute the mean value of a diagonal observable, takes in a diagonal observable in dictionary, list of matrix format. Oh, so it actually does semi-value is the value of observable for state I. So as an example, the ZZ of qubits can be given as, so you give it matrix diagonal. Okay, so this is just this. Okay, just one function. Distance. Hellinger fidelity. Isn't this? I think this is what Amir is using in the quantum computing dojo. Is it? What's this actually? Oh yeah, definitely. I'm seeing again. I'm seeing again some lag as well on my side. Well, at least. So he is explained in the documentation actually. Computes the Hellinger fidelity between two counts distributions. Okay. Where h is the Hellinger distance. The value is bounded dimension 0, 1. Yeah, but I don't know what it is. I wanted to have a better definition of this. That it's... Isn't there anything in the Wikipedia for that? Hellinger distance. In probability, the Hellinger distance closely related is used to quantify the similarity between two probability distributions. Okay, that's all I needed to know. It's defined in terms of the Hellinger integral, which is... Okay, so it's an integral. Okay, cool. So it's just to know how similar two probability distributions are. Yeah, I mean, I hate this because Europe is telling me all the time that there's gonna be buffering, and I don't know if this is something that is affecting. Let me check quickly on the phone how this looks like before I go on. There's going to be buffering, and I don't know if this is something that is okay. Looks good. Looks good. Thought it would be worse. The Europe thing here is that the thing here is just crappy. It's pretty crappy. Anyway, so we've got the Hellinger fidelity in here. I'm not interested in how is this calculated right now. It kind of gives you the, so it calculates the sum of values, and then it basically seems like it's calculating these here, the square root of these minus these. Okay, it's a distance. It's how to calculate how two different probability distributions are similar to each other. So there's some analysis and stuff. And okay, make observable. What is this? Make observable. Convert an observable in matrix form to dictionary form. A dictionary with all observable states as keys and corresponding values being the observed value for that state. And that is what it returns, the dictionary. I guess that's what, I guess this is something like, you know what, I think I'm going to switch here because I can at least here, that was an analysis, I can search across. So I can easily, can I close the terminal? I think so, yeah. I think it's going to be easier if I switch. If this is not going to die. Why do I always have to have such problems? Okay. What is the input though? Observers to be converted to dictionary form. Search basically in terms of what is being used anywhere else, or is just a helper function for building dictionaries for matrices and lists? Okay, yeah, it's used in average, because that's what I was thinking. Yeah, okay. It takes a dictionary, yeah, because it actually can take the observable, like the ZZ, and then it turns it into an observable. Was it like... What does it do? It converts an observable in matrix form to dictionary form. Okay, yeah. So that's all in terms of analysis. What about operators? Okay, so this is where it gets a bit more trippy. So we've got like random base operator, measures, where to start, channel, symplectic, whatever that means. And now it's giving me the error again. Let's see. Yeah, okay. It takes a dictionary, yeah, because it actually can take the observable, like the ZZ, and then it turns it into... okay, so it seems you might... my video maybe is really buffering, but I guess you're getting, or at least if I try my phone, you should be getting the audio fairly well, which is what kind of matters. Good. Where was I? Not here. So now we've done the analysis folder, the operators folder, quaternions, base operator. It's an abstract base operator class. What is these? Subset dimensions are equal, probability dimension, number of qubits if an n-qubit operator or none otherwise. Absolute tolerance parameter for float comparisons. This is all long. Reshape. Return a shallow copy with reshape input and output subsystems dimensions. Base operator. Then we have custom iterator. What is this? These methods should be overfilled as the conversions of iterator only. Okay, it's just some kind of iterator. Measures. Collection of useful quantum information functions for operators. Okay. I guess the idea of this folder is that you've got a way to create your own operators, like sort of more advanced operators. So process fidelity. Okay, so in here there's a bunch of stuff you can kind of apply to your operator. So you process the fidelity. Is instance. Okay, that's more like a util. What else do we have in here? This instance average gate fidelity of a noisy quantum channel. But how does it know the average gate fidelity? Like, what is this? Operator, super operator. Okay. I came across the concept of a super operator before. If the channel and target do not have the same dimensions, or have different input and output dimensions. So this is one of the errors it gives back. Operator and super operator. Quantum channel. Wikipedia. We're going to do quantum super operator. Wikipedia. So these are things to explore, definitely. Quantum channel, super operator. In quantum information theory, a quantum channel is a communication channel which can transmit quantum information as well as classical information. An example of quantum information is the state of a qubit. An example of classical is a text document transmitted over the internet. Okay, more formally, quantum channels are completely positive trace-preserving maps between spaces of operators. In other words, a quantum channel is just a quantum operation viewed not merely as the reduced dynamics of a system, but as a pipeline intended to carry quantum information. Some authors use the term quantum operation to also include trace decreasing maps, while reserving quantum channel for strictly trace preserving maps. Suppose two parties A and B wish to communicate in the following manner. A performs the measurement of an observable and communicates the measurement outcome to B classically. According to the message he receives, B prepares his quantum system in a specific state. In the Schrödinger picture, the first part of the channel simply consists of A making a measurement. It is the observable map, okay? If, in the event of the ith measurement outcome, B prepares his system in state R, the second part of the channel takes the above classical state to the density matrix. Okay, so it's a... Okay, that gets funky though, right? Like, it's a way to add your classical information in a density matrix. In quantum teleportation, a sender wishes to transmit an arbitrary quantum state of a particle to a possibly distant receiver. Consequently, the teleportation process is a quantum channel. Okay, so teleportation as a... Okay, so you can understand teleportation as an operator, or as a super operator. No, as a quantum channel. Sorry, I'm mixing things up here. The apparatus for the process itself requires a quantum channel for the transmission of one particle of an entangled state to the receiver. Teleportation occurs by a joint measurement. I guess what this means is just a mathematical way to kind of reason about the system. Like, because in here you've got like quantum stuff, but you've also got classical things. And so what you want to do is, I guess, you want to be able to... Kareem, may I help? Hey, actually, I mean, guys, anything that you want me to take a look at, or I don't know, it's not that I'm looking for help. I'm just kind of like, browsing around the code. So, and kind of coming across, like, the idea, my idea was, for those who are joining now, is like, if, um, instead of, trying to see what can I do with Qiskit, or what can I build with Qiskit based on what I know about quantum computing, I'm kind of trying to do it the other way around. So taking a look at Qiskit's source code and see what concepts are in there that I am not aware of, and then I kind of, we'll add them to the list, and maybe kind of, do a digging in Wikipedia maybe, or something like that. So yeah, I mean, if you have any comments on what I'm watching, or you want to take a look at some particular parts of the code, let me know. I think I'm gonna still be around for like half an hour or so calmly. I'm gonna do definitely more sessions on these. I'm kind of really thinking about doing this, turning this into a bit of a weekly thing. So I kind of learn about, at least, I want to come across different concepts, and kind of expand the my current my current, I don't know, understanding of what are the concepts in the field that are worth taking a look at. So quantum channel is what I was trying to kind of um, get a basic understanding of, and so it seems to be kind of a mathematical construct, or a construct to kind of be able to deal with quantum stuff and classical stuff at the same time, if I'm correct, but I'm not so sure. For a pure quantum system, the time evolution at a certain time is given by these by the is that the density matrix? Yeah, where is the Hamiltonian T's time? Mm. A state viewed as the mapping from observables to their expectation values is an immediate example of a channel. Is it? Mm. We will assume for the moment that all the state spaces of systems in the classical quantum are finite dimensional. The memoryless in the section title carries the same meaning as in classical information theory. The output of a channel at a given time depends only upon the corresponding input, and not any previous ones. Okay, so that actually goes... Important examples. No, there's channel capacity. Okay, but I think that's not something that I'm gonna dig into right now more. But it's quantum channel. And a super operator is a linear operator acting on a vector space of linear operators. Sometimes... So is it maybe an operator of a quantum channel? Maybe. Sometimes the term refers more specially to a completely positive map which preserves or does not increase the trace of its arguments. It's in the field of quantum computing, quantum programming. The use of super prefixes in no way related to its other use in mathematical physics. Okay, so it's nothing to do with supersymmetry and superalgebra. Lindblad superoperator. Quantum superoperator example. Of linear operators. So, so it's an operator that acts on operators. That is really confusing. I mean, if anyone knows what is this about, or anyone has some useful resources to dig into this, then I'll be super happy. But because where was this here? Channel. So it's quantum channel. Okay, so I guess this is kind of one of the things you can do with the with this quantum info package, right? Like you can actually do some more funky stuff, like like work with quantum channels. Gate error. Diamond norm. What is the diamond norm? Dimension of input. Yeah, that's that. I didn't expect. What is all these? Okay, those are funky. Those are like. What is these? CVXPY. Is this an abbreviation or is this an actual thing? Oh, it's a Python embedded modeling language for convex optimization problems. It allows you to express your problem in a natural way. Okay. What is convex optimization problems? A convex optimization problem is a problem where all of the constraints are convex functions, and the objective is a convex function of minimizing, if minimizing, or a concave function if maximizing. Okay. Convex problems. Linear functions are convex. So linear programming problems are convex problems. Okay. So this is using then some, it's using these for some of the optimization stuff. I guess. CVX BMAT. Complex matrix areas. So this is some like pretty advanced stuff, I think. Okay, that's part of the diamond norm. Okay, cool. And what is the diamond norm? Man, I know nothing. Boy, I know nothing. Diamond norm. In quantum information, the diamond norm is a distance metric between quantum operations. Informally, the diamond norm measures the single-use distinguishability of the operations. If a player is randomly given one of two operators permitted to pass one state through the unknown operator, and then measures the state in an attempt to determine which operation they were given, then the amount that such player can bias their success probability by from 0.5 is proportional to the diamond norm between the two operators. Okay, the trace distance between output states of the respective operations maximized over all possible input states, including entangled with qubits that are not being operated on. Okay, so it's basically a distance metric between quantum operations. So how far an operation is from another. Okay, I guess that kind of is useful for whatever stuff you might be wanting to compare. I don't know, you're building operators. I really have no idea. Like, I'm so far away, disconnected from all these quantum channels, super operators, but still the super operator part is a bit like I'm not sure I understand what it means. It's an operator that an operator that operates on the operator space, right? So what it does what it turns operators into operators. So what do people in the chat say? The documentation here is more organized and a bit intuitive. Make American think harder. Yeah, definitely. uh, Not American though, but yeah. Um, yeah, I guess the documentation is probably better. I just want to take a look at the code. I think I don't know. Sometimes you can dig some interesting stuff, and it just just like to browse the code, kind of get familiar with the folder structures, see where things are, and what um, operator. This is the matrix operator class. Okay, so that's basically a matrix operator. So you can use this class to, I guess, build your operator. Is instance data from label the enqueued operator. String. Okay, so you're giving it like a okay, so you're giving it a predefined label, and it kind of creates that for you. Um, okay. It has functions for, okay, to instruction to operator, conjugate, transpose, compose. The operator self at other. So you can compose operators together. That's cool. This means like compose, for example, a Hadamard gate and the next gate or something like this. As if like you would kind of run them in one single moment or something. Oh yeah, okay, so it's equal to these, yeah. Okay, cool. So you can compose operators like these. It's good to know you can do that. I mean, I don't know if it's really useful, but for me, but okay. What else? Dot. Okay, that's the dot product, I guess. Power. So you can have that power. You can kind of have a concrete power. Can n be? It's an integer. Okay. Tensor. The tensor product of this operator and another operator. Expand. Okay, so that's other times self. Add. Multiply. Yeah, basically some stuff in there. Shape. Tensor shape of the matrix operator. So this basically gives you a matrix operator. A super operator is a okay. So what is Jose saying? A super operator is a completely positive trace decreasing linear map. Page 12. Thank you. Yeah, sorry. It's because I don't have a math background. Like super is a completely positive trace decreasing linear map. Like that doesn't really tell me anything intuitively in terms of what is it like. Is it an operator? Is it something that you can that helps you turn an operator into another operator in terms of like, or is it something that works together with quantum channels? That's yeah. Comments are delayed. I'm sorry. It's I think it's I don't know if I can tweak these next time. I don't know if I can tweak the delay, but there seems to be always a bit of a delay. So I'm sorry for these. I'll have to dig into these. I'm kind of seeing the chat comments a bit later because it says about like a couple minutes ago. Yeah, I don't know. We'll see. Anyway, thanks for bringing some of the comments. I'm looking for the super operator stuff. I'm looking for something a bit more informal. I'm not here for the formality. I'm not here for the math. I just want to kind of understand. I want to grasp some of those concepts that I'm not aware of, so I can plan. What are other topics that I could dive into or study. Maybe that's just not for me. Like maybe that like level, that advanced level, it's not something that I want to get into necessarily. It's just too close to the actual physics from a utility perspective. Like study quantum channels and things like this. I mean, I guess if quantum teleportation can be considered a channel in of itself, some of these things could be useful to actually study stuff around teleportation, but I don't know. Okay, so we've got Pauli tools for working with Pauli operators. Class Pauli. Set vectors, arguments, from label. Okay, so that's the same idea, from label, from bool. Oh, as in like the Z and the X being true or false. I'll put the Pauli label. Equality, multiplication, complex multiplication. Multiply two Paulis and track the phase. Returns the Pauli, the multiplied Pauli, and the sign of the multiplication. Okay. Why do you get it like separate though? Two matrix, update Z, partial entire Z. What is this? Self. Z to be updated Z, indices to be updated qubit indices. What is this though? What does it mean to update partial or entire Z? Like, is there documentation for these? Updates at Qiskit. I guess I probably want to have in there. Qiskit. No, that's basically generated stuff. Okay, so it's the same that I see in the code. Mm. Where is this used in? Is this used in any examples? I mean, I haven't cloned the other Qiskit packages, but okay, so just in the tests, yeah. Test equality operator, different Paulis. Or is it just a helping function for testing stuff? No. No, that's deep copy updates it. What does it say updates it for? I really don't get it. This update X, insert Paulis, insert or append Pauli to the targeted indices. Append Paulis at the end. But at the end of what? Delete qubits? Random. Return a random Pauli. Okay, so back at it. Pauli single. Generate single qubit Pauli at index with Pauli label. So one thing that I don't get is why you have all this index thing in here. Is it that you have like a set of qubits and you're kind of with this class you can compose like a gate made of Paulis or something like this? I keep forgetting what the Chronicle product is. Is it just the what is it? Keep forgetting. Oh yeah, okay. It's these thing. It's the I think I'm calling it, yeah, okay, outer product, yeah. Oh, so this is a generalization in terms of kind of tensors. Okay, it's for the tensor product, yeah. Because the outer product is for matrices and vectors. Okay. So yeah, exactly. So it's you multiply B per each component of A. Yeah. Okay, cool. Okay. Pauli group, return the Pauli group with the phases have been removed. Case weight is ordered by Pauli weights and case tensor is ordered by... Maybe I should clone. I will do that. Maybe not in the... Okay, so wait a second. Jose is saying, roughly speaking, it is more complicated. T is a super operator and M a positive matrix. Hence, the trace of Tm is smaller than the trace of M, trace decreasing. And Tm is a positive matrix, nearly completely positive. Okay. I guess either more comments are coming or yeah, I'll have to dig into this. I'm not so sharp with math at that level. I mean, I know it's not a really high level, but I'm feeling a bit rusty with all these here about Pali groups and like and this comments of phases being removed and whatnot. I really don't understand what case weight case tensor is ordered by IX and the counting lowest qubit fastest. I can't really imagine like use cases, you know, where something like this is useful. And I guess I should probably um, clone the other. So wait a second. This is used in other places. And oh, okay, in state visualization. Okay, let's take a look. So. Oh, is it just utilities? Okay, so that just gives you the Pali group back. Is it just language utilities? Okay, I get it. So that just gives you a okay, it just gives you a it gives you the set of the Pauli gates, and then um, okay, if you give it like if you say 2 qubits, right, like you're gonna have all these different combinations, right? Identity, 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 and the NOT gate, identity and Y gate, identity and Z gate, X and identity, etc. Okay. Okay, I get it. So back here, Pauli predicates, predicates for operators. What are these predicates? Matrix equal is square matrix, is diagonal matrix, is symmetric, is Hermitian, is positive. So these are all a bunch of utilities to doing fancy stuff. Is unitary matrix, is isometry. Okay. There's something to deal with quaternions. Using quaternions, okay. Normalize. Why would this be useful? Why would this be useful? I'm curious. I'm literally lost here. I don't really know anything about quaternions, so. So basically, yeah, I don't know. Random. Okay, this creates random operators. A random unitary. Oh, that's nice. Okay, random Hermitian. Those are useful stuff, I guess. A random quantum channel. Okay. This constructs the Stein spring operator for the quantum channel by sampling a random isometry from the unitary Haar measure. What is this? What is this? Let me go back here. So Stein spring factorization. The church of the larger Hilbert space. Huh? I don't know what the Stein or Stein spring is. Wikipedia. So Jose keeps writing, roughly speaking. Okay, so the Pauli group is the the fourth dimension generation of the multiplicative group in the complex plane. Pauli matches essentially the unit quaternions. Okay. Quaternions. I'm not sure I understand where is this coming from though. Man, I'm feeling such a noob right now. But okay, this is kind of the supposed to be the stuff where there's some more advanced things to I guess build experiments and do stuff. So you kind of can build custom operators and do things with it. Quantum channel operator. It returns a quantum channel operator. I'd like to know what is these though. Like, just because it's a concrete example. But is a result from operator theory. Okay, that is something. So what am I reading? Is a result from operator theory that represents any completely positive map on a C star algebra as a composition of two completely positive maps. Okay, I definitely stepped into something that is way beyond. I've seen this as well before. Diamond norm, I forgot already that. Diamond norm, I think this was the distance between quantum operators. Yeah. Then the quantum operator, the Hellinger distance. Okay, we know this. Quantum operator, super operator is what was still not clear completely. It acts on a vector space of linear operators. Okay. Scalar OP. This is a symbolic representation of a scalar identity operator on multiple subsystems. It may be used to initialize a symbolic scalar multiplication scalar identity operator. What is this? Conjugate transpose is unitary to matrix tensor. So that is a concrete operator. Pad with identity. What is this? Scalar op. It inherits from base operator, and it's a symbolic representation of a scalar identity operator on multiple subsystems. It's an identity operator, so used to initialize a symbolic scalar multiplication of an identity and then be implicitly converted to another kind of operator subclasses by using the compose dot tensor. Is this used somewhere within Terra? Okay, so in the density, I see super operator. No, I see scalar. Okay, so this is something here. There is something that combines the super operator and the scalar operator. Reset, the state of a subsystem to the zero state. So it creates a reset super operator as a super operator. Okay, and that's an identity with coefficient 0. Okay, so it seems the scalar operator is just a way to generalize the identity. I say, what else is Jose saying? I'm sorry, Jose, because I can't really. The comments seem to come like in a big delay, and I'm not like. The idea of Pauli matrices came from the representation of the angular momentum. This algebra appears because the spin is superposition of two values. Yeah, I think I know what you mean. But I don't know if it's really what I was kind of asking, as in like I was. Let me go back. I'm trying to understand what a super operator is. Like it's like really from at an intuitive level. Okay, like I'm not like I don't want to get too formal with these. So I can see here in the code that to reset a density matrix, they are basically, so Qiskit is creating a super operator, kind of based off of a scalar operator with coefficient 0, which I guess is it just a matrix with all zeros? Because that's what I understand the scalar operator is an identity matrix with whatever dimensions you give it, and then what you do is you evolve yourself, you do self-evolve, so it seems like you're evolving the density matrix with these super operator. But I don't get like the okay, so the super operator is the operator that you is an operator, right? Okay, so the super operator is just an operator. It's just maybe the form that the super operator takes is the one that is useful to evolve a density matrix, for example. Maybe that's it. Maybe that's it. Um, yeah, maybe that's it. I don't know. This would be something to take a look at. And I could be here for hours. I feel like I just started and it's like an hour already. But I'm gonna stay around for a bit more. So there's some more comments. A map from operator to operator. Okay, a map from operator to operator. But what is it useful for? That should be a positive matrix, operator TH, super operator. I'm legit being taught by experts on on a live stream, and I really have. I'm sorry because I'm not at the level. I'm just trying to understand everything at a really intuitive level. So it's a map from an operator to operator. So it maps operators to operators. Okay. Yeah. So it just transforms an operator to another one, I guess. I'm just maybe confused by the notion of an operator in here. Maybe I understand an operator being. I understand an operator being a like say like a Pauli, like an X gate, right? Like that would be an operator. And so a super operator would be an operator that takes my NOT gate and turns it into a Z gate, for example. I don't know. Or is it what I said, like that it's an operator to operate with density matrices, for example? Because I never understood the density matrix as, it being an actual operator. I thought the density matrix is just a way to represent the state, but I never thought of it as this being an operator. That's what's confusing me a little bit. Pen instruction. Take a positive matrix to another positive matrix, Jose says, and decreases the trace. This is a super operator. This is almost a super operator because positive is not enough. It should be completely positive. Super operators are useful because positive matrices with trace below or lower, less or equal than 1 are mixed quantum states. A super operator transforms a mixed quantum state into another quantum state. Okay, so here we're really talking about the density matrix as being an actual. Superoperators are useful because positive matrices with trace and mixed quantum states transforms a mixed quantum state. Okay, instead of evolution of states, now we can use a super operator to study the evolution of a density matrix. Okay, cool. So here the quantum channel that takes row to row prime will be characterized by a superoperator. Okay, I get it. I get it. Um, yeah, that's nice. Thank you. Thanks, Jose. I think that's okay. It makes sense. I'm sorry because I know that you guys want to really help out and like um, I really want to kind of make sure that I truly understand like at the deepest level. Um, but I'm really floating. I'm really floating at the surface right now, and I really don't want to dig too much into it. I just wanted to kind of get the what's the essence of it. Okay, so it's an operator that kind of helps me to evolve a density matrix, for example. Okay, so I can literally create a super operator from like any operator. Like I can kind of up level up an operator. So I can take an X operator, like an X gate, and turn it into super operator, and that's what's going to then help me move the density matrix. To be honest, I don't fully understand density matrices. I mean, I know how they're built, and I know how to read the diagonal, but I don't really know what's the physical meaning of a density matrix. Like, I don't really know what it why are we like why the diagonal is really the one that represents the actual, like I don't know what it means to kind of like how do you interpret that, how do you read the density matrix in terms of um, yeah, I don't know what to say. I don't know how to explain it, like because in the IBM Q experience you kind of see the density matrix, the columns and the rows having the labels of states, and that's what kind of confuses me, I think. So I know that I know what they are useful for. I know how to read them, but I feel I'm not really um, super into really understanding them intuitively uh, in a way that I feel I'm a bit more fit with it. Okay, but um, so I've just gone through operators. Okay, now in states there's density matrix stuff. Um, is a point in the sphere. Ah, it's a point inside the ball. Okay. There's a point inside the block sphere. I never thought of it this way. That's really interesting. I never thought of it this way. So I know with the density matrix, I know you can deal with mixed states, right? This means a system like it's basically an ensemble of possible pure states, right? Like because of noise and all that stuff. It's just a point in the ball. Okay. I never thought of it this way. Thank you. I think that's super. That's actually really helpful. Uh, for 1 qubit, right? Like that's what you're saying inside the blocks here for 1 qubit. Okay. Yeah. In the edge, sort of in the surface of the sphere, that will be a pure state. Okay. You could still express a pure state in a density matrix form, though. Cool. Thank you, guys. That's super helpful. Density matrix quantum state class. Okay, so there's an actual density matrix state. Okay. So that's actually, oh man, that's really good. Thank you. That is basically, so what you're saying is with density matrix, let me try something real quick. So basically what you're telling me, right, is that if I go and create an entangled state, like a messy one, I don't know, let me just do this and maybe these and maybe these, right? Like, so I cannot measure, I cannot, like, this is something that Quirk tells me it's incoherent, right? And so, but I can put a density matrix in here. because that really tells me probability of 1, probability of 0, 0. But that doesn't tell me anything about phases. That tells me something about the state, the state of the subsystem. It's the density matrix is for algebraists and point inside the ball is for geometers. Yeah, nice. Point inside the ball on the sphere, pure inside mix. What are you saying? Pure state and points in the sphere, Majorana stellar representation. I don't know what is it. What is that? N qubits pure state and points in the sphere. Yeah. Okay. Aha. That's the name of the. Right. For example, 100 is pure. Yeah. 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 I mean that's still pure, right? I can't. I think I can. I can get like mixed states in here in Quirk. But it could be interesting to actually extend that. Yeah, thanks. I think it's. I definitely want to dig into these. Don't want to take too much of your time right now. I definitely want to dig into these density matrices. Sort of. Okay, I never thought about the relationship between the geometric relationship. So these being as a way to represent. Yeah, those are states inside the blocks here actually. States, measures, state fidelity. Definitely want to take a look at these as well. 3 qubits, 3 points in the sphere. Okay. Okay, so here you can calculate the purity of a quantum state. Okay, so this is probably, yeah, it's a trace of, it returns the trace of the squared density matrix. Okay. And that tells me how pure it is. Another thing that I don't fully understand is when people talk about like the amount of entanglement that there is, like I don't really understand what this amount of entanglement means. Like how can you relate these? Like what does it mean? Like what does it mean to have more entanglement or less entanglement? Like I understand the concept of entanglement, but not like the how much entangled you are. Mutual information. Bipartite state. That is the mutual information between two systems. Namely, for example, if the two systems are entangled, like how much information is encoded in the actual relationship or entanglement. Entanglement entropy is higher. Okay. So the more entanglement, the more entropy, or? Cool. Measures quantum state. It's tied up with the other. Yeah, I get it that it's more tied up, as in like maximum entangled if they cannot be entangled with another Z. So there's actually, okay, I get it. So there's actually a sense of how much you can entangle, right? Like if you've maximally entangled a qubit, this qubit cannot be entangled with anything else without losing that maximal entanglement with, like if I entangle these two qubits, like those are maximally entangled right now. Can I get rid of this? Exactly. So now if I would want to entangle the first qubit, sorry, my mouse is not working well. What's going on? If I would want to entangle these with another qubit, then then these two do not, they are not maximally entangled anymore, because I've had to share that somehow. I think that's what you're saying. That's cool. Okay. Yeah, I'm gonna leave it here. It's it's gonna be late. It's gonna be late here. Um, no, if you collapse Qubit 1 into 0, the other gets to 0. Ah, that is what it means to be maximally entangled. So you mean that the other one actually fully collapses as well? I don't know. Mm. Thanks, guys, for helping out in these. I mean, I have done less than I thought I would, but it's at the end of the day. I mean, that's really I'm gonna be doing these. I'm gonna be trying to do these regularly, at least once a week. Kind of, run around the Qiskit source code and kind of see what I stumble upon in terms of concepts. At least I'm happy I took a bit of a, you know, uh, an attempt to understand kind of the quantum channel, the super operator stuff, the density matrices. Okay, so you can really work with these concepts in Qiskit as well. That is, can you do this with Circ, for example? Circ quantum channel. It seems like, okay, so there's actual... Yeah, okay, because I guess that's a necessary abstraction when we talk about noise models, right? Like, I guess. Channel mixture channel stabilizer effect. Pauli expansion. Look at the fourth advanced school in computer science and engineering on the mathematics of quantum computation. Cool, thank you. Yeah, I'll definitely take a look at those references. It's been really helpful. Thank you a lot, guys. I'm gonna stop here now. It's been cool. I don't know. It was a bit of an experiment. I didn't know how this will work out. Um, I'm kind of, I will be doing these anyway, so I thought, why not sharing it with people? Just running around the Qiskit's code. So I'm right now at Terra and Quantum Info. I've barely scratched the surface in here. As in, like, what can you do with Qiskit? We've seen analysis operators and kind of barely started with states. And what is synthesis? One qubit decomposed, two qubit decompositions. Oh, those are decompositions of gates. Local invariance, I guess. Scheduler result. Okay. But it doesn't seem to be anything else other than, like, okay, stuff for quantum state. So can you just take a state and kind of like do some advanced stuff, like evolve the state or something? Oh, nice. Okay, so you can actually work, you can actually query for probabilities and stuff like that. Sample memory. Okay, cool. I'm gonna leave it here, guys. Thanks a lot for watching. It's been a bit of a long stream, but I kind of liked it. Yeah. I'll be doing this more often. I'll definitely be doing this more often, and I think the live stream format kind of fits into these as well. I mean, I kind of like if there are some people that want to ask or that want to help me kind of in the journey of browsing the code. Yeah, that always helps. So, having said that, have a good day, guys, and see you next week on another session on inspecting Qiskit source code. It's been fun. It's been cool.